Imagine a star so dense that a teaspoon of it weighs billions of tons. These are neutron stars, the strangest objects in the universe. But what exactly are they, and how much do we truly know about them? In this video, we'll dive into everything science has uncovered so far. If you enjoy it, please like, subscribe, and share. And tell us in the comments which fact about neutron stars amazed you the most. Thank you for watching. Now let's begin. A neutron star begins its existence in the death of a massive star. The life of such a star extends over millions of years, during which it fuses lighter elements into heavier ones in its core. At first, hydrogen fuses into helium, a process that provides pressure to counter gravity. Later, helium fuses into carbon and oxygen, and in the most massive stars the sequence continues through neon, magnesium, silicon, and other nuclei. Each stage takes less time than the previous one because the energy yield from fusion decreases. The final step is the buildup of an iron core. Iron nuclei are tightly bound and cannot release energy through fusion or fission. Once the center is dominated by iron, fusion no longer supports the weight of the star. Gravity becomes unopposed. As the iron core grows to about 1.5 times the mass of the Sun, it reaches a critical point. The pressure from degenerate electrons packed so tightly that quantum rules stop them from being compressed further, can no longer resist collapse. The core suddenly implodes. In less than a second, the radius shrinks by thousands of times. During this collapse, electrons are forced to combine with protons in a process called electron capture. Each reaction produces a neutron and a neutrino. The core becomes enriched with neutrons while an enormous flood of neutrinos streams outward. The density quickly rises to nuclear values, around a few times 10 to the 14 grams per cubic centimeter. At this density, neutrons strongly repel one another at short ranges, halting the collapse. The inner core rebounds slightly, sending a shock wave outward. The shock initially loses energy as it encounters the infalling outer layers and as neutrinos escape. For decades, astrophysicists debated whether the shock would stall permanently or if some mechanism could revive it. Current simulations show that heating by neutrinos, combined with convection and instabilities behind the shock, provides the energy needed to drive the outer layers away. The result is the spectacular explosion known as a core collapse supernova. The central object left behind is a neutron star. It is incredibly small compared to the original star, measuring only about 20 kilometers across. Yet it contains between 1 and 2 times the mass of the Sun. The density is so great that a sugar cube volume of neutron star matter would weigh hundreds of millions of tons. The structure is unlike any normal material. Atomic nuclei are crushed together, electrons vanish into protons, and the star becomes a giant sphere of neutrons with a thin outer crust of nuclei and electrons. The conservation of angular momentum ensures that the newborn remnant spins rapidly. If the progenitor's core rotated once every several days before collapse, the reduction in size increases its spin rate by many orders of magnitude. Some neutron stars emerge with rotation periods of tens of milliseconds. Others spin even faster, close to hundreds of times per second. The centrifugal force from such rapid rotation remains far weaker than gravity, so the star stays intact. But the rotation profoundly shapes how the star radiates. The magnetic field also grows enormously. As the stellar core shrinks, magnetic flux is conserved, forcing field lines closer together. A core that had a modest field like the Sun's may, after collapse, host a field exceeding 1 trillion Gauss. In rare cases, the amplification may be even greater, producing magnetic fields stronger than 1 quadrillion Gauss. These extreme fields influence the star's radiation, particle acceleration, and the stresses in its crust. The first moments after birth are marked by intense neutrino emission. Nearly all of the gravitational binding energy released in collapse, about 10% of the star's mass energy, escapes as neutrinos in the first tens of seconds. Earth-based detectors have confirmed this. When a supernova appeared in the Large Magellanic Cloud in 1987, underground detectors recorded a burst of neutrinos. This brief signal matched the predictions of collapse models and demonstrated that a neutron star had likely formed at the heart of that explosion. The supernova also expels the outer layers of the progenitor star into space. The debris expands at thousands of kilometers per second, forming a glowing supernova remnant. Shock waves heat the ejected gas, making it shine in X-rays and radio waves. The remnant spreads heavy elements such as carbon, oxygen, silicon, and iron into the interstellar medium. These elements eventually mix with clouds of gas, enriching the raw material from which new stars and planets form. The Crab Nebula, which was born from a supernova observed in the year 1054, is one of the best-known remnants. At its center lies a neutron star that still rotates 30 times each second. Its winds of energetic particles continue to illuminate the nebula centuries after the explosion. Some newborn neutron stars are visible as pulsars. The combination of rapid spin and strong magnetic field creates beams of radiation that sweep across space. When these beams cross Earth, radio telescopes record a train of pulses. The first such object was discovered in the 1960s. Its perfectly regular pulses, arriving every second and a third, initially puzzled astronomers. No known star could behave that way. The realization that it was a rotating neutron star opened a new window on the universe. Pulsars became precise laboratories for studying dense matter and strong gravity. In the earliest years after formation, the neutron star continues to change. The crust cools and solidifies. Neutrino emission dominates for the first million years before photon emission from the surface becomes the main cooling channel. The rotation gradually slows as magnetic torques extract energy. The initial conditions set at birth, mass, rotation, and magnetic field, determine the later observable behavior. Some remain active pulsars, some evolve into magnetars with explosive magnetic outbursts, and others become faint, cooling remnants detectable only with sensitive X-ray observatories. The environment around the newborn star is equally dynamic. The outward-moving shock heats the surrounding gas, and sometimes drives fresh shocks into the interstellar medium. Interaction between the expanding debris and the surrounding material creates intricate structures of filaments and knots. Radio and X-ray images reveal turbulence and clumps where faster and slower ejecta collide. In a few cases, astronomers can trace the kick velocity imparted to the neutron star during birth. Many neutron stars receive a strong recoil from asymmetries in the explosion, shooting them through the galaxy at hundreds of kilometers per second. Observations across the electromagnetic spectrum build a picture of these birth events. In optical light, astronomers record the fading glow of supernovae. In X-rays, satellites detect hot plasma in remnants. In radio, telescopes map the expanding shells and search for pulsars. In neutrinos, rare but valuable detections confirm the energy released during collapse. Each type of observation adds another detail to the story. Together, they show that when a massive star exhausts its fuel and its core implodes, the result is a compact object unlike anything else in the cosmos. The neutron star that emerges is hot, dense, rapidly rotating, and strongly magnetized. Around it spreads the debris of the destroyed star, glowing for thousands of years as it cools and disperses into space. The remnant stands as a witness to the catastrophic collapse and as a new astrophysical laboratory of matter under conditions impossible to reproduce on Earth. The structure of a neutron star is layered, with each region defined by pressure, density, and the kinds of particles that can exist under those conditions. The outermost part is a thin atmosphere only a few centimeters thick. This layer consists of electrons and light nuclei and determines the radiation that escapes into space. Beneath this atmosphere lies the outer crust. Here, nuclei are arranged in a crystalline lattice with a sea of electrons moving between them. The density is already far beyond that of ordinary solids, climbing to values where a single cubic centimeter contains more matter than a mountain. In the outer crust, nuclei are still relatively normal, consisting of protons and neutrons bound in familiar ratios. As one moves inward, the density increases. At around 10 to the 11 grams per cubic centimeter, it becomes energetically favorable for neutrons to leak out of the nuclei. This marks the beginning of the inner crust. In this region, nuclei coexist with free neutrons and electrons. The nuclei become extremely neutron-rich, far beyond what can be created in terrestrial laboratories. The free neutrons form a fluid that pervades the lattice, giving the inner crust unusual properties. It is neither a pure solid nor a simple liquid, but a mixture of both. At still higher densities, approaching half the density of atomic nuclei, the lattice structure becomes unstable. The nuclei begin to deform, elongate, and connect into shapes that are neither spherical nor uniform. These exotic arrangements are known collectively as nuclear pasta, because their shapes resemble sheets, tubes, and droplets reminiscent of lasagna, spaghetti, or gnocchi. The reason for these structures lies in the competition between the strong nuclear force, which prefers to keep nucleons close together, and the repulsion of protons, which favors separation. The balance creates intermediate geometries that minimize the system's energy. Nuclear pasta is thought to be one of the strongest materials in the universe, far surpassing steel in rigidity. Beneath the pasta region, matter becomes uniform. At these densities, the distinction between individual nuclei disappears. Neutrons dominate, with a small fraction of protons and electrons to maintain charge balance. This is the outer core of the neutron star. The density in the outer core ranges from roughly nuclear density up to a few times greater. The state of matter here is extremely uncertain, since it cannot be reproduced in laboratories. Nevertheless, models suggest that neutrons may form a superfluid, flowing without resistance, while the small number of protons may form a superconductor. These quantum states change how the star transports heat and angular momentum. Deeper still lies the inner core, where densities exceed several times that of an atomic nucleus. Here, theoretical possibilities diverge. Some models predict that neutrons remain the dominant component, perhaps with exotic mixtures of hyperons, which are particles containing strange quarks. Other models propose that matter undergoes a phase transition to deconfined quarks, where individual protons and neutrons dissolve into their constituent quarks. The exact equation of state, which describes how pressure depends on density, remains uncertain. Different models predict different radii, masses, and responses to compression. Observations of neutron star masses and radii provide indirect evidence that helps to rule out some models and favor others. The equation of state is crucial because it governs the star's macroscopic properties. For instance, a stiff equation of state where pressure rises quickly with density produces larger radii for a given mass and allows higher maximum masses. A soft equation of state where pressure rises more slowly produces smaller radii and lower maximum masses. The true behavior of dense matter sets the Tolman-Oppenheimer-Volkoff limit. the maximum mass that a neutron star can have before collapsing into a black hole. Precise measurements of neutron star masses, especially those close to two solar masses, rule out equations of state that are too soft. The crust and core together create a layered star with unique physical behavior. The crust is elastic, able to support mountains only millimeters high under enormous gravity. The crust can fracture under magnetic or rotational stresses, releasing energy that may appear as starquakes. The inner crust, with its sea of neutrons, allows superfluid vortices to pin to the lattice. When these vortices suddenly move, the rotation of the star can jump slightly, an event known as a glitch. Such glitches are observed in pulsars and provide evidence for the presence of superfluid matter inside. Thermal transport is also affected by the star's structure. The crust has lower thermal conductivity than the core, so after a neutron star is born hot, heat flows outward and the surface gradually cools. Cooling observations, measured in X-rays, trace how temperature declines with age and provide indirect clues to the internal composition. Stars with more efficient neutrino emission in the core cool more quickly. This allows astronomers to compare theory with observation and infer whether exotic particles or processes exist in the dense interior. The layered structure also affects magnetic fields. The field is anchored in the crust and the core, and its long-term evolution depends on whether protons form a superconductor and how electric currents flow. If the protons are superconducting, magnetic flux is quantized into tubes that interact with neutron superfluid vortices. This interaction may couple the magnetic field to the rotation of the star, affecting how the field decays. Over millions of years, the magnetic field may weaken, but the rate depends strongly on the microphysics of the core and crust. In summary of the physical picture without drawing conclusions beyond this section, the neutron star interior transitions from an outer crust of nuclei and electrons to an inner crust with free neutrons, then into a core of uniform dense matter whose exact composition remains unknown. Each region introduces new forms of matter and new physical phenomena, from nuclear pasta to quantum superfluids. These layers are not merely theoretical. Their presence explains observed behaviors such as glitches, cooling patterns, and magnetic field evolution. The challenge is to probe such inaccessible conditions using only the light and particles that reach Earth. Observatories play a central role in this effort. X-ray satellites measure thermal emission from the surface, revealing cooling rates. Radio telescopes monitor pulsars for timing irregularities that betray the movement of superfluid vortices. Gravitational wave detectors constrain the equation of state by measuring how deformable neutron stars are when they merge. Each line of evidence points back to the same question. What is the true behavior of matter at densities several times higher than atomic nuclei? The structure described here, crust, pasta, outer core and inner core, provides the framework within which these questions are asked and interpreted. The existence of such layers with their strange and extreme states of matter shows that neutron stars are not uniform spheres but complex laboratories. Their architecture is central to understanding every observed property, from radiation to rotation. The description of these regions is therefore the basis for interpreting the wealth of data that continues to accumulate from telescopes and detectors across the world and in space. Inside a neutron star, the conditions of density and temperature allow matter to enter quantum states that have no counterpart in ordinary solids or liquids. The neutrons, which are electrically neutral particles, can pair up at low temperatures in a way similar to how electrons form pairs in superconductors on Earth. When neutrons pair, they form a condensate that flows without viscosity. This is called a neutron superfluid. The protons, although they are a small fraction of the total, are charged and can also form pairs. When they do, they create a superconducting component. These states are supported by the immense densities in the star, far higher than anything that can be created in terrestrial laboratories, and they remain stable over millions of years. The presence of a neutron superfluid has important consequences for the star's rotation. In a superfluid, angular momentum is not distributed smoothly, but is carried by quantized vortices. Each vortex is a microscopic tube around which the superfluid circulates. In the core of a neutron star, billions upon billions of such vortices exist. They arrange themselves into a lattice that keeps the rotation organized. Over time, as the star loses energy and slows its spin, the vortices must migrate outward. If they are pinned to the crust or to magnetic structures, their movement is impeded. When they eventually break free, they can cause a sudden adjustment in rotation. This produces the observed phenomenon called a pulsar glitch, where the rotation period abruptly changes. These glitches provide direct observational evidence for the presence of superfluid matter inside neutron stars. The superconducting protons influence the star's magnetic field. In a superconductor, magnetic flux cannot be distributed uniformly. Instead, it is quantized into narrow tubes of magnetic field known as fluxoids. These fluxoids thread the star's core, and they may interact with the neutron vortices. If a vortex moves outward, it can drag a fluxoid with it, altering the magnetic field distribution. Conversely, the fluxoids can pin the vortices, making it harder for them to move. This coupling between superfluid vortices and superconducting flux tubes may be a key mechanism by which the star's magnetic field evolves over time. Thermal evolution is also shaped by these quantum states. In a neutron superfluid, the emission of neutrinos changes dramatically. Certain reactions that would normally produce neutrinos are suppressed because of the energy gap created by pairing. However, when pairs break and form, neutrinos are released. This makes the cooling curve of a neutron star highly sensitive to whether superfluidity is present and at what densities it occurs. Observations of surface temperatures compared to ages have shown evidence that supports the presence of superfluid neutrons and superconducting protons. For example, the young neutron star in the Cassiopeia, a supernova remnant, appears to be cooling faster than standard models predict, which has been interpreted as the onset of neutron superfluidity in the core. The crust is also influenced by these quantum effects. The free neutrons in the inner crust form a superfluid that permeates the nuclear lattice. This superfluid can flow through the lattice without friction, but it can also become trapped in the structure, leading to stored angular momentum. When that momentum is suddenly released, it contributes to glitches. The study of glitches across many pulsars has shown a range of behaviors, with some stars glitching frequently and others rarely. These variations likely reflect differences in the extent of pinning and the distribution of superfluid regions. Another consequence of superconductivity is the possibility of long-term stability of magnetic fields. If the protons in the core are superconducting, the magnetic field lines are confined to the fluxoids. The mobility of these fluxoids determines how the field evolves. If they move slowly, the field can be preserved over billions of years. If they drift or are expelled, the field can decay more rapidly. This distinction may help explain why some neutron stars maintain strong fields over long timescales, while others fade. Models also predict that different pairing states may occur at different densities. Neutrons can pair in singlet or triplet states, depending on the orientation of their spins and their relative momentum. These states have different critical temperatures and therefore influence cooling and dynamics in distinct ways. Determining which states occur in real neutron stars is a major challenge, but observations continue to refine the possibilities. Laboratory experiments cannot recreate the exact conditions of neutron star interiors, but nuclear physics provides constraints. Studies of nuclear matter, heavy ion collisions, and theoretical calculations of nucleon interactions help to estimate pairing gaps and superfluid properties. The combination of these calculations with astrophysical observations allows scientists to narrow the range of models that describe dense matter. In terms of energy, the transition to superfluidity and superconductivity releases latent heat and modifies the neutrino emissivity. This means that the timing of when these transitions occur in a star's life has a direct effect on its thermal history. The onset of neutron pairing may cause a sudden acceleration in cooling, as observed in some young neutron stars. Superconducting protons alter the specific heat capacity and conductivity, shaping how temperature gradients evolve from core to crust. The behavior of superfluids and superconductors in neutron stars also has implications for gravitational wave emission. If the motion of vortices or the configuration of flux tubes is uneven, the star's shape may deviate slightly from perfect symmetry. Even tiny deformations can produce continuous gravitational waves as the star rotates. Searches for such signals are ongoing with detectors like LIGO and Virgo. While no detection has yet been made, the limits already constrain how large these deformations can be. Another possible outcome of superfluid behavior is the phenomenon of precession, where the star's rotation axis wobbles. If the superfluid and the crust are not perfectly coupled, differential rotation can develop. This can change the observed timing of pulsars and provide further insight into the interior. Although evidence for long-term precession is tentative, some pulsars show modulations consistent with such behavior. Overall, the existence of superfluid neutrons and superconducting protons inside neutron stars provides a coherent explanation for several observed phenomena: glitches, magnetic field evolution, cooling behavior, and possibly gravitational wave emission. These quantum states, while exotic, follow naturally from the physics of strongly interacting particles at extremely high density and low temperature. They represent one of the clearest examples of quantum mechanics operating on astrophysical scales. In the neutron star's crust and core, then, the interplay of superfluid vortices and superconducting flux tubes governs both microscopic and macroscopic behavior. Each observed pulse, each timing regularity, and each cooling curve reflects this invisible but powerful quantum machinery at work inside the star. The study of these effects continues to connect theoretical nuclear physics with precise astronomical observation, forming one of the most direct bridges between the smallest and the largest scales in the physical universe. The mass and radius of a neutron star are among its most fundamental properties. Together they reflect the underlying equation of state, the relation between pressure and density of dense matter. Observationally, determining these values is difficult, since the stars are tiny compared to the distances at which they are observed. Nevertheless, multiple approaches provide constraints, and when combined they form a coherent picture of what is possible and what is ruled out. The Tolman-Oppenheimer-Volkoff limit sets the maximum mass. It arises from the balance between gravity and internal pressure. When mass exceeds this limit, not even the stiffest equation of state can prevent collapse into a black hole. The exact value of the limit depends on the microscopic physics of dense matter. Calculations predict values in the range of about 2 to 3 solar masses. Discovering neutron stars with masses at the high end of this range can therefore eliminate softer equations of state that cannot support them. One of the most precise methods to measure mass comes from binary systems, especially double neutron star binaries and systems where a neutron star orbits a white dwarf. The timing of pulsar signals provides exquisite measurements of orbital parameters. General relativity predicts effects such as Shapiro delay, the extra time taken by pulses as they pass near a companion, and periastron advance, the rotation of the orbit's closest approach. These relativistic effects allow the masses of both objects to be determined. Several pulsars have masses close to 2 solar masses, notably the millisecond pulsar J0 4 plum to 32. The existence of such massive neutron stars already rules out many equations of state that predict collapse at lower masses. Radius measurements are more challenging. The radius affects how light and radiation escape from the surface, but disentangling it from other variables requires careful modelling. X-ray observations of thermonuclear bursts on accreting neutron stars provide one route. During these bursts, the luminosity briefly reaches the Eddington limit, where radiation pressure balances gravity. By analysing the cooling tail and the apparent surface area, astronomers can infer radius estimates. Another method comes from quiescent neutron stars in globular clusters. These stars accrete slowly or not at all, and their thermal spectra, fitted with atmosphere models, provide constraints on radius. Uncertainties remain due to the distance, atmosphere composition, and magnetic field, but the results generally suggest radii of about 11 to 13 kilometers. More recently, the Neutron Star Interior Composition Explorer, or NISA, on the International Space Station has provided another line of evidence. NISA measures X-ray pulse profiles from rotating hotspots on the star's surface. As the star rotates, the hotspot comes in and out of view. The way the light curve is modulated depends on the bending of light by the star's gravity, which in turn depends on the ratio of mass to radius. By modelling these pulse profiles with general relativistic ray tracing, NISA provides direct constraints on both mass and radius simultaneously. The first results, for the pulsars J0030 plubs 4551 and J0740 pulsar indicate radii of around 12 kilometers. These measurements are consistent with a relatively stiff equation of state that allows large radii and supports high masses. Another source of information comes from gravitational wave astronomy. When two neutron stars spiral together, their shapes are slightly deformed by tidal forces. This tidal deformability affects the gravitational wave signal during the inspiral. The event GW170817, detected by LIGO and Virgo in 2017, provided the first such measurement. The data showed that neutron stars are not extremely compact, ruling out very soft equations of state that would give radii below 10 kilometers. When combined with mass measurements, these tidal constraints narrow the allowed region of the mass-radius diagram. The importance of the mass-radius relation lies in its direct connection to microphysics. Each proposed equation of state corresponds to a unique curve in the mass-radius plane. Observations populate this plane with points and regions. As the data improve, entire classes of equations are excluded. For example, models that predict early onset of exotic particles like hyperons often soften the equation of state too much, leading to maximum masses below 2 solar masses, and are therefore inconsistent with observations. Models with extremely stiff behavior that predict radii above 15 kilometers are also ruled out. The remaining viable models describe matter that is moderately stiff, capable of supporting at least 2 solar masses while keeping radii near 12 kilometers. The Tolman-Oppenheimer-Volkoff limit itself is a theoretical construct, derived from the equations of general relativity applied to a spherical distribution of matter. It provides an upper bound on mass for a given equation of state. Observationally, the heaviest precisely measured neutron stars approach 2.1 solar masses. If future discoveries reveal stars closer to 2.3 or higher, this would significantly constrain theories, as only the stiffest equations could support them. Conversely, if no stars are found above 2.1 solar masses, that may imply the true maximum is not far beyond. Gravitational wave detections of massive mergers will continue to refine this picture. The interplay of mass and radius is also evident in stability. A neutron star with too little mass, below about 1 solar mass, may not form at all because collapse requires sufficient core mass. At the high end, exceeding the limit produces a black hole. Between these extremes, the range of possible stars is determined by the pressure-density relation of matter. Each neutron star observed with its specific mass and inferred radius is therefore a test of nuclear physics under extreme conditions. The crust also plays a role in defining the observable radius. Although the crust contains only a few % of the total mass, its thickness affects the star's radius by a kilometre or more. Models of nuclear symmetry energy, which describes the energy cost of having unequal numbers of neutrons and protons, influence crust properties. Experiments on heavy nuclei in terrestrial laboratories provide constraints that complement astrophysical measurements. The symmetry energy at nuclear density and its slope with increasing density connect laboratory nuclear physics with neutron star structure. As measurements improve, the overlap between laboratory constraints, pulsar timing, X-ray modeling, and gravitational wave data grows stronger. This convergence is gradually mapping out the true equation of state. The progress has been rapid in recent decades, moving from broad speculation to precise numbers with error bars. Each new observation tightens the allowed space, bringing physicists closer to a definitive description of matter at supranuclear density. The measurement of both mass and radius is essential, since either quantity alone is insufficient to discriminate between models. A heavy star with a small radius points to very different physics than a heavy star with a large radius. Only by combining both can the true behavior be identified. This is why multi-messenger astronomy, drawing from electromagnetic, gravitational and particle observations, is central to neutron star research. The balance between gravity and pressure that defines the Tolman-Oppenheimer-Volkoff limit is not merely theoretical. It manifests in the observed population of stars, the signals of mergers, and the structure inferred from radiation. Neutron stars thus provide one of the most direct ways to study the properties of matter under the most extreme conditions known, with mass and radius measurements as the primary tools. Neutron stars can be observed most clearly when they manifest as pulsars. A pulsar is simply a rotating neutron star whose magnetic axis is tilted relative to its rotation axis. The strong magnetic field channels charged particles along its lines and accelerates them to relativistic speeds. As the particles move, they emit radiation, primarily in radio frequencies but also at higher energies such as X-rays and gamma rays. Because the magnetic axis and the rotation axis are not aligned, the emission is confined to beams that sweep across the sky. When one of these beams crosses the Earth, telescopes detect a sharp pulse of radiation. Each rotation produces 1 or 2 pulses, and the sequence repeats with extraordinary regularity. The geometry of pulsar emission has been studied for decades. The lighthouse model, in which beams sweep like the rotating beam of a beacon, remains the basic explanation. The pulse profile seen from Earth depends on the angle between the rotation axis, the magnetic axis, and the observer's line of sight. Some pulsars produce simple single-peaked pulses, while others show multiple peaks. In the radio band, pulses are often narrow, lasting only a small fraction of the rotation period. At higher energies, the emission can be broader. The diversity of pulse shapes reflects both geometry and the complex physics of the magnetosphere. The stability of pulsar periods is remarkable. Some millisecond pulses rival the precision of atomic clocks, with timing stability that makes them valuable for navigation and for searching for gravitational waves. The regularity arises because the star is a rigid object with immense inertia. Its rotation slows only gradually as energy is lost through electromagnetic radiation and particle winds. The slowdown rate, or spin down, is measurable and provides a way to estimate the pulsar's magnetic field strength and age. The so-called characteristic age is obtained by dividing the period by twice the rate of change of the period. While this is only an approximation, it offers insight into the evolutionary state of a pulsar. Not all pulsars spin steadily. Some show glitches, sudden increases in spin frequency. These are thought to result from the dynamics of superfluid vortices inside the star, which suddenly transfer angular momentum to the crust. Glitches are observed most commonly in young pulsars, such as the Vela pulsar, where they can occur every few years. The size of glitches varies, with some producing changes in frequency of only a part in a billion, and others far larger. After a glitch, the spin usually relaxes toward its previous trend, suggesting a complex interplay between the interior superfluid and the solid crust. Other pulsars show timing noise, irregular variations that do not fit a simple model. The origins of timing noise remain under study. Possible causes include magnetospheric processes, irregular torque applied by particle winds, or long-term changes in the interior. Some pulsars switch between different states of emission, with timing behavior changing accordingly. These state changes reinforce the connection between interior physics and magnetospheric output. The discovery of pulsars in the late 1960s provided the first direct evidence of neutron stars. Jocelyn Bell Burnell and Anthony Hewish detected a series of unusually regular radio pulses from the sky. At first, the source was jokingly referred to as a possible signal from extraterrestrial intelligence, but it quickly became clear that it was a natural object. The pulses were too rapid and stable to be explained by any normal star. The idea of a rotating neutron star fit the observations perfectly. This breakthrough transformed astrophysics by proving that these compact remnants were real and could be studied systematically. Since then, thousands of pulsars have been catalogued, with periods ranging from milliseconds to several seconds. Millisecond pulsars are thought to be old neutron stars that have been spun up by accretion of matter from a companion in a binary system. The accretion transfers angular momentum, reducing the rotation period to a few thousandths of a second. These objects are extremely stable and are used in pulsar timing arrays to search for gravitational waves from supermassive black hole binaries. In contrast, young pulsars like the Crab pulsar have longer periods and higher spin-down rates, reflecting their youth and strong magnetic fields. The emission of pulsars spans the electromagnetic spectrum. While they were first discovered in radio, observations have extended to X-rays and gamma rays. Satellites such as the Fermi Gamma Ray Space Telescope have revealed that many pulsars emit bright gamma ray beams, often with different pulse profiles from their radio emission. This indicates that the high-energy radiation is produced in different regions of the magnetosphere. Models include outer gap and slot gap scenarios, where particle acceleration occurs near the light cylinder, the region where the co-rotation speed would equal the speed of light. These models continue to be refined as new data arrive. Pulsar beams are not visible from every orientation. For every pulsar detected, there may be several that remain unseen because their beams do not intersect Earth. The total number of neutron stars in the galaxy is therefore much larger than the known pulsar population. Estimates suggest that there may be around 100 million neutron stars in the Milky Way, though only a few thousand are observed as pulsars. This beaming fraction complicates efforts to estimate the full population, but radio surveys and population models attempt to correct for it. Pulsars also serve as astrophysical tools. Their precise timing allows tests of general relativity in binary systems. where the orbital decay due to gravitational wave emission has been measured. They can act as probes of the interstellar medium, since their signals are dispersed by free electrons along the line of sight. By measuring dispersion, astronomers map the distribution of ionized gas in the galaxy. Millisecond pulsars in particular are cornerstones of pulsar timing arrays, networks of radio telescopes that monitor many pulsars simultaneously to detect the low-frequency gravitational wave background. The diversity of pulsar phenomena continues to grow. Some pulsars emit giant pulses, burst far brighter than their normal emission. The Crab pulsar is a notable example. Others show mode switching, in which the pulse profile changes abruptly between distinct patterns. Nulling pulsars occasionally stop emitting altogether for minutes or longer before resuming. Intermittent pulsars switch on and off over timescales of months. Each of these behaviors reflects changing conditions in the magnetosphere and adds complexity to the simple lighthouse picture. The precise mechanisms that generate the radio emission of pulsars remain a topic of study. The coherence of the radiation suggests collective plasma processes, but the exact details are debated. Observations of polarization, frequency dependence, and pulse microstructure provide clues. Understanding the emission process is key not only for pulsar astrophysics, but also for interpreting fast radio bursts, some of which may be related to neutron star activity. The rotation-powered pulsars thus reveal the dynamic link between the interior, the magnetosphere, and the observable signals. They stand as some of the most useful and accessible examples of neutron stars, showing how a compact, dense, rapidly rotating object can produce beacons detectable across the galaxy. Their study continues to refine knowledge of dense matter, strong magnetic fields, and plasma processes under extreme conditions. The magnetosphere of a neutron star is the region around it where the magnetic field dominates the motion of charged particles. In ordinary stars like the Sun, magnetic fields are strong enough to shape plasma flows in the outer layers, but in neutron stars the situation is far more extreme. With surface magnetic fields typically 1 trillion times stronger than the Earth's, even the tenuous plasma near the star is forced to follow magnetic field lines. The rotation of the star winds the field into complex shapes, and the interaction between the star's rotation and its magnetic field governs how energy is lost and how particles are accelerated. The geometry of a neutron star's magnetosphere can be understood by beginning with a rotating magnetic dipole. Close to the surface, the field resembles that of a simple bar magnet, with closed loops near the equator and open lines extending outward from the poles. As one moves farther from the star, rotation becomes increasingly important. There exists a characteristic radius called the light cylinder, defined as the distance from the rotation axis where the co-rotation speed would equal the speed of light. Beyond this radius, field lines cannot remain closed because plasma cannot move faster than light. The magnetosphere must therefore open up, carrying away energy and particles in a pulsar wind. Within the magnetosphere, charged particles are accelerated to high energies in regions called gaps. These are places where the density of charges is insufficient to screen the electric field induced by the rotating magnetic field. In these gaps, strong electric fields accelerate electrons and positrons to relativistic speeds. As they move along curved field lines, they emit gamma rays. These photons can then convert into electron-positron pairs in the intense magnetic field, a process called pair production. The result is an avalanche of particles that fills the magnetosphere with plasma. This plasma flows outward along the open field lines, forming a relativistic wind. The creation of pairs is crucial because it supplies the magnetosphere with the charges necessary to support the currents that maintain the global field structure. Without continuous pair creation, the magnetosphere could not sustain itself. The details of where and how pairs are produced remain an active area of research. Competing models suggest that pair cascades may occur near the stellar surface above the magnetic poles in so-called polar caps, or in outer gaps near the light cylinder. Observations of gamma-ray pulsars, particularly by the Fermi Gamma Ray Space Telescope, are helping to discriminate among these models by comparing predicted light curves with observed ones. As the pulsar wind streams into the surrounding medium, it forms a pulsar wind nebula. The wind is composed of relativistic electrons, positrons, and magnetic fields. When it collides with the ambient interstellar medium or with supernova ejecta, a termination shock forms. At this shock, particles are further accelerated and emit synchrotron radiation across the electromagnetic spectrum. The Crab Nebula is the prototypical example. Its bright dynamic structure is powered entirely by the central pulsar, which injects energy into the nebula at a rate of more than 10 to the 38 ergs per second. X-ray images from observatories such as Chandra show wisps, jets, and rings in the Crab Nebula, revealing the continuous outflow of energy from the pulsar to its surroundings. Not all pulsar wind nebulae are as bright or symmetric. Some neutron stars move rapidly through the interstellar medium due to a kick imparted at birth. In these cases, the wind interacts asymmetrically with the gas ahead of the moving star, producing a bow shock. These bow shock nebulae appear as comet-like structures trailing behind the neutron star. The study of such nebulae provides information about both the pulsar wind and the density of the surrounding medium. The structure of the magnetosphere also influences the timing of pulsars. The torque that slows rotation arises from currents in the magnetosphere that connect to the star's surface. Changes in plasma density or field configuration can therefore change the braking torque, leading to timing irregularities. Some pulsars switch between states of higher and lower spin-down rate, correlated with changes in their radio emission profile. This shows that the magnetosphere is not static but can reorganize itself on humanly observable timescales. Another aspect of the magnetosphere is its role in radiation mechanisms. Radio emission, although not fully understood, is thought to be generated by coherent processes in the plasma streaming along open field lines. High-energy emission in X-rays and gamma rays is produced by curvature radiation, synchrotron radiation, and inverse Compton scattering. The relative contributions of these processes depend on location within the magnetosphere. By modeling the light curves and spectra, astrophysicists can infer where the dominant emission zones are located. The plasma processes in magnetospheres are so complex that they require large-scale numerical simulations. Particle-in-cell simulations, which track the motion of millions of charged particles in electromagnetic fields, have become a major tool. These simulations reproduce pair cascades, current flows, and the global structure of the magnetosphere, connecting microscopic physics to observable signals. The results show that the basic dipole model must be supplemented with current sheets, reconnection regions, and dynamic plasma behavior. The energy carried away by the magnetosphere is substantial. Over time, the rotational energy of the neutron star is steadily drained by electromagnetic radiation and particle winds. This spin-down powers pulsar emission and nebulae. The rate of spin-down is measured precisely from pulsar timing and provides a direct probe of the energy loss. The efficiency of converting spin-down power into radiation varies among pulsars, with some radiating most of their energy as gamma rays, while others channel more into particle winds. Magnetospheres are also linked to fast, bright phenomena. Some neutron stars emit giant pulses, extremely bright bursts of radio emission that occur sporadically. These may be connected to reconnection events or sudden changes in current flows within the magnetosphere. Similar processes are invoked in some models of fast radio bursts, suggesting that magnetospheric activity in highly magnetized neutron stars could be responsible. The study of magnetospheres bridges astrophysics and plasma physics under conditions that cannot be replicated in laboratories. The strengths of the fields, the energies of the particles, and the scales of the structures are unique to neutron stars, yet the fundamental processes, electric fields, magnetic fields, particle acceleration and radiation, are the same as those studied on Earth. By comparing observations with theory, scientists can apply well-tested principles to this extreme environment. When neutron stars are embedded in supernova remnants, their magnetospheres continue to evolve as they interact with the expanding shell. Over thousands of years, the nebula may fade, leaving an isolated pulsar with only a bow shock to reveal its presence. Over millions of years, as the spin slows and the magnetic field decays, the magnetosphere weakens, and the star becomes invisible to telescopes. Throughout this evolution, the magnetosphere serves as the interface between the dense, exotic interior of the neutron star and the vast, diffuse interstellar environment. In this way, the magnetosphere is not merely a byproduct of strong fields and rapid rotation, but the active region where energy is converted, radiation is produced, and the star's influence extends outward. The geometry of open and closed field lines, the cascades of particle creation, the winds and nebulae, and the bow shocks are all manifestations of this interaction between matter and field. Each observation of pulses, nebula structures, or timing changes is a window into the dynamics of the magnetosphere. The radiation emitted by neutron stars spans an enormous range of energies, from low-frequency radio waves to the most energetic gamma rays. The mechanisms that produce this radiation depend on the motion of charged particles in intense magnetic and electric fields. Because these fields are so strong, and because the particles are accelerated to nearly the speed of light, the resulting processes are extreme versions of those familiar in laboratory and space plasma physics. Understanding them requires tracing the pathways by which energy stored in rotation and magnetic fields is transferred into light. One of the primary mechanisms is curvature radiation. Charged particles moving close to the speed of light along curved magnetic field lines are forced to accelerate toward the center of curvature. This acceleration produces electromagnetic radiation. In neutron star magnetospheres, the field lines curve tightly, so the emitted photons can reach very high energies. Curvature radiation is thought to be a major contributor to the gamma-ray emission observed from many pulsars. The efficiency of this process depends on both the radius of curvature of the field lines and the energy of the particles. Observations of light curves and spectra in gamma rays, especially from the Fermi telescope, match the expectations of curvature radiation in outer regions of the magnetosphere. Another key process is synchrotron radiation. When relativistic electrons spiral around magnetic field lines, they emit photons tangential to their paths. The energy of the emitted photons depends on both the particle's energy and the strength of the magnetic field. In neutron stars, the magnetic field is so strong that synchrotron photons can extend into the X-ray range. Synchrotron emission is prominent in pulsar wind nebulae, where relativistic particles from the star's magnetosphere are further accelerated at shocks and radiate as they spiral through magnetic fields. The Crab Nebula's broadband spectrum extending from radio to gamma rays is dominated by synchrotron processes. Cyclotron radiation is a related process that occurs when charged particles spiral in quantized energy states in a magnetic field. In neutron stars, especially in accreting systems, cyclotron absorption and emission lines can be observed in X-ray spectra. These cyclotron resonance scattering features provide direct measurements of magnetic field strength near the stellar surface. Values inferred from these features typically confirm magnetic fields of about 1 trillion Gauss, in agreement with estimates from spin-down measurements. Such observations give rare direct access to conditions very close to the neutron star surface. Inverse Compton scattering adds another mechanism. In this process, relativistic electrons collide with low-energy photons, boosting the photons to higher energies. In neutron star environments, seed photons may come from the surface, from accretion disks, or from synchrotron emission. When these photons encounter high-energy electrons, they can be upscattered into X-rays or gamma rays. In some accreting neutron stars, inverse Compton processes dominate the observed spectra, producing hard X-ray tails that extend to hundreds of kilo-electron volts. The interplay of these processes produces the complex emission profiles observed. For instance, in rotation-powered pulsars, radio emission is thought to be generated by coherent plasma processes near the magnetic poles, while higher energy emission comes from curvature and synchrotron radiation further out in the magnetosphere. In accreting systems, cyclotron lines and Comptonization dominate. In magnetars, bursts and flares produce spectra, shaped by resonant scattering in twisted magnetospheres. Each mechanism reflects the underlying physics of particle acceleration, field geometry, and plasma density. The coherence of radio emission remains a puzzle. Normal incoherent processes like synchrotron radiation cannot produce the observed brightness temperatures, which exceed limits by many orders of magnitude. This implies that large numbers of particles radiate in phase, amplifying the signal. Models propose that plasma instabilities in the open field line region of the magnetosphere create bunches of particles that emit coherently. Evidence for this comes from the fine time structure of pulses, down to microseconds, and from the high degrees of polarization observed. The details remain uncertain, but the phenomenon illustrates the complexity of plasma physics in strong fields. In high-energy emission, spectral cutoffs and shapes provide clues about where the radiation originates. Gamma-ray pulsars observed by Fermi typically show spectra with exponential cutoffs at a few giga-electron volts. This is consistent with curvature radiation in outer magnetospheric gaps. The alignment or misalignment of radio and gamma-ray pulses constrains the geometry of the emission zones. For some pulsars, gamma-ray pulses lag behind radio pulses, suggesting emission at larger radii. For others, the two are nearly aligned. Modeling these differences helps to refine theories of where particle acceleration occurs. The observational signatures of cyclotron lines in accreting X-ray pulsars are especially valuable. When matter flows along magnetic field lines onto the magnetic poles, the electrons in the accretion column experience quantized energy levels due to the strong field. Photons resonantly scatter off these electrons, producing absorption features in the spectrum at energies directly proportional to the magnetic field strength. The detection of such lines has provided some of the most direct measurements of neutron star magnetic fields. Over time, changes in the line energies can even track variations in the accretion flow and the field configuration. Inverse Compton processes reveal themselves in broad-band spectra of X-ray binaries. When accreting matter forms a hot corona around the neutron star, low-energy photons from the surface or the disk pass through this region and gain energy. The result is a spectrum that extends beyond the thermal emission expected from the surface alone. By fitting such spectra, astronomers infer temperatures and optical depths of the coronal plasma. These parameters inform models of how matter flows and how radiation escapes near the star. The combination of these mechanisms explains why neutron stars appear so different across contexts. Isolated pulsars, accreting X-ray binaries, and magnetars all emit light, but the dominant processes vary. What unites them is the basic principle: charged particles moving in strong magnetic and electric fields radiate efficiently across the spectrum. The extreme densities and fields of neutron stars amplify familiar processes into regimes never seen elsewhere. Radiation mechanisms also connect to cooling. After a neutron star is born, its hot surface emits thermal X-rays that gradually fade. Observations of this cooling emission require careful separation of thermal and non-thermal components. Non-thermal radiation from magnetospheres or accretion can mask the thermal glow. By focusing on isolated middle-aged neutron stars with faint magnetospheric activity, astronomers can measure the cooling more directly. The thermal spectrum is often modified by the atmosphere, which may consist of hydrogen, helium, or heavier elements. Modelling these atmospheres is necessary to translate observed spectra into surface temperatures. Each mechanism, from curvature to Compton scattering, has been confirmed or constrained by observations across decades. Together they form the toolkit by which neutron stars are revealed to telescopes. Without these processes, the stars would be invisible in the dark. Instead, they shine as radio beacons, X-ray bursters, gamma-ray pulsars, and sources of cyclotron lines. The study of radiation mechanisms continues to refine knowledge of both the stars themselves and the plasma processes that govern their behavior. Among neutron stars, a special class stands out for its extreme magnetic fields and explosive behavior. These are called magnetars. While typical neutron stars have magnetic fields around 1 trillion Gauss, magnetars can reach field strengths of 1 quadrillion Gauss or more. Such fields are the most intense known in the universe. They dominate the dynamics of the star's crust and magnetosphere, storing enormous amounts of energy that can be released suddenly in bursts and flares. The discovery of magnetars arose from the observation of unusual X-ray and gamma-ray sources in the late 20th century. These sources produced bursts far more energetic than those seen from ordinary pulsars, and their properties suggested that only ultra-strong magnetic fields could power them. The crust of a neutron star is solid, but it is under constant stress from the magnetic field. In magnetars, the field is so strong that it strains the crust almost to breaking. When the stress exceeds the crust's yield strength, cracks or shifts occur. These starquakes can rearrange the magnetic field configuration and release energy. The energy travels outward as both seismic vibrations through the star and as disturbances in the magnetosphere. The result is a sudden bright burst of X-rays and gamma rays that can last from fractions of a second to minutes. The most dramatic events are called giant flares. In these, the luminosity can exceed that of the Sun by a factor of 1 trillion, albeit for a very brief time. Such events are rare but have been observed, notably in 1979, 1998 and 2004, when magnetars in our galaxy and nearby galaxies produced giant flares that were detected by satellites across the solar system. Between these outbursts, magnetars emit persistent X-rays that are much brighter than would be expected from rotation alone. This emission is thought to be powered by the decay of the magnetic field. The twisted field lines heat the crust and the atmosphere, producing thermal and non-thermal radiation. The decay of such ultra-strong fields occurs more rapidly than in ordinary neutron stars, so magnetars are relatively young, with ages of thousands to tens of thousands of years. Their high persistent luminosity and bursting behavior distinguish them from rotation-powered pulsars, which are generally older and less luminous in X-rays. The magnetosphere of a magnetar is also unique. In ordinary pulsars, the field is close to a dipole, with open and closed regions. In magnetars, the field is often twisted and unstable. The twisting drives electric currents that populate the magnetosphere with dense plasma. Resonant scattering of surface photons by this plasma produces characteristic X-ray spectra with hard tails extending to high energies. Observations by satellites such as XMM Newton, Chandra and NuStar have revealed these features, confirming that magnetar magnetospheres are filled with highly energetic particles. The bursts themselves show a range of timescales and intensities. Short bursts, lasting less than a second, are the most common. Intermediate flares can last several seconds and release more energy. Giant flares are the rarest and most powerful. During the brightest giant flare recorded, in 2004 from the Magnetia SGR 1806-20, detectors on multiple spacecraft were saturated by the initial spike, and the blast even affected Earth's ionosphere. Such events demonstrate the colossal energy stored in magnetic fields. The afterglow of a giant flare often shows quasi-periodic oscillations, interpreted as vibrations of the neutron star crust or magnetosphere. These oscillations provide a possible probe of the star's interior structure, although the data are limited. Magnetars also exhibit timing irregularities. Like pulsars, they spin down as they lose rotational energy, but the rates are larger, reflecting their strong fields. Their periods are typically between 2 and 12 seconds, much longer than most pulsars. Some magnetars show glitches, while others undergo sudden changes in spin-down rate associated with bursts. These variations reveal that the processes in the interior and magnetosphere are tightly coupled. The connection between magnetars and other phenomena has become an active field of research. One intriguing possibility is that magnetars are the engines behind some fast radio bursts, brief flashes of radio waves lasting milliseconds that have been observed at cosmological distances. In 2020, a fast radio burst was detected from the direction of a galactic magnetar, SGR 1935-2154, linking at least some fast radio burst to magnetar activity. The mechanism may involve magnetic reconnection events or crustal shifts that launch intense radio emission. This connection suggests that magnetars could be responsible for many of the fast radio bursts observed in other galaxies. Another link is to superluminous supernovae and gamma-ray bursts. Some models propose that when a magnetar is born with both a strong magnetic field and rapid rotation, the injection of its energy into the surrounding supernova can make the explosion unusually bright. In other cases, a rapidly spinning magnetar formed in a stellar merger could power short gamma-ray bursts. These scenarios remain under investigation, but they highlight the potential role of magnetars in some of the most energetic cosmic events. Observations continue to expand the catalogue of magnetars. As of now, only a few dozen are known, but they represent a distinct population. Their distribution in the galaxy indicates that they are young and often associated with regions of massive star formation. Their high magnetic fields may originate from dynamo processes during the proto-neutron star stage, when rapid rotation and convection amplify seed fields to extreme strengths. Not every neutron star becomes a magnetar, suggesting that specific birth conditions are required. This study of magnetars combines multiple observational approaches. X-ray satellites track bursts and persistent emission. Radio telescopes search for pulses or bursts associated with magnetars, though most are radio quiet. Occasionally, magnetars turn on as radio pulses for limited periods. Optical and infrared observations probe their environments and associations with supernova remnants. Each detection adds detail to the picture of how magnetic energy is stored and released. Magnetars are valuable astrophysical laboratories because their behavior directly reveals the interplay of magnetic fields, crustal mechanics, and plasma processes. By analyzing their bursts, scientists learn about how matter behaves under stress and how magnetic reconnection works in extreme fields. By studying their persistent emission, scientists probe the decay of magnetic fields and the heating of dense matter. The connection to fast radio bursts offers a new window into cosmological phenomena, potentially linking small-scale physics with observations across billions of light years. The defining characteristic of magnetars is that their energy output is dominated not by rotation or accretion, but by magnetic fields. This sets them apart from all other neutron star classes. The decay of their fields and the release of stored magnetic energy drive everything from persistent X-rays to catastrophic giant flares. Their relatively small number in the galaxy is balanced by the extraordinary phenomena they produce, making them among the most fascinating and extreme objects known in astrophysics. When a neutron star resides in a binary system, it can accrete matter from its companion. This process gives rise to some of the brightest X-ray sources in the sky, known collectively as X-ray binaries. The behavior of accretion depends on the nature of the companion star and the geometry of mass transfer. In systems with a low-mass companion, matter is drawn from the outer layers of the companion through Roche-Lobe overflow. The material forms an accretion disk around the neutron star, gradually spiraling inward as friction and viscosity transport angular momentum outward. In systems with a high-mass companion, the neutron star may capture material from the stellar wind. This inflow of gas is less orderly, but can still feed the neutron star with enough matter to produce luminous X-ray emission. As the gas moves inward, gravitational energy is released. The potential energy of matter falling toward the neutron star is immense because the radius of the star is so small. Even before reaching the surface, the energy release per unit mass is a significant fraction of the speed of light squared. This energy is converted into heat and radiation, making accretion onto neutron stars one of the most efficient power sources in astrophysics. The result is X-ray luminosities that can exceed 10 to the 38 ergs per second, rivaling or surpassing the total output of millions of ordinary stars. In low-mass X-ray binaries, the accretion disk is central. The disk becomes hot due to friction and radiates in X-rays. As matter spirals inward, it eventually reaches the innermost stable regions close to the neutron star. Because neutron stars have solid surfaces and strong magnetic fields, the final stages of accretion differ from those around black holes. The inflowing gas is funneled by the magnetic field lines onto small regions near the magnetic poles. There, the material crashes into the surface at nearly a third of the speed of light, forming hotspots that radiate intense X-rays. The rotation of the star causes these hotspots to move in and out of view, creating pulsations in the X-ray light curve. Such objects are known as accretion-powered pulsars. In high-mass X-ray binaries, the neutron star interacts with the strong wind from its massive companion, often an O or B star. The wind consists of streams of gas driven outward by radiation pressure. When the neutron star orbits within this wind, some of the gas is gravitationally captured and accreted. The accretion is less steady than in disk-fed systems, leading to variability on timescales from seconds to days. In some cases, dense clumps in the wind cause sudden increases in X-ray brightness. The study of these variations provides insights into both the neutron star's magnetosphere and the structure of the companion's wind. Boundary layers form where the accretion disk meets the neutron star surface. In this region, the gas must decelerate from nearly Keplerian orbital speeds to match the rotation of the star. The dissipation of energy in the boundary layer produces additional X-rays, often with spectral features distinct from those of the disk or the hotspots. Observing these spectra allows astronomers to study the physics of accretion flows under extreme gravity. Accretion also has long-term consequences for the neutron star's spin. Matter carries angular momentum, and as it settles onto the star, it can spin the star up. This process is believed to be responsible for the existence of millisecond pulsars. Over time, Accretion from a companion star can reduce the rotation period from seconds to a few milliseconds. Once accretion ceases, the neutron star can shine as a rotation-powered millisecond pulsar, with remarkable timing stability. Thus, accretion not only powers luminous X-ray emission, but also recycles neutron stars into a new evolutionary state. The interaction between magnetic fields and accretion flows creates diverse phenomena. In some systems, the magnetic field is strong enough to disrupt the disk far from the surface. The inner edge of the disk is truncated, and matter is forced to follow magnetic field lines onto the poles. In weaker field systems, the disk may extend nearly to the surface before being channeled. The balance between magnetic pressure and ram pressure of the inflowing gas determines the geometry. This interplay gives rise to observable differences in timing and spectral properties. Accreting neutron stars also show quasi-periodic oscillations in their X-ray light curves. These are subtle, rapid variations in brightness that reflect processes near the star. Some oscillations occur at kilohertz frequencies, suggesting that they arise from orbital motion in the innermost regions of the disk. By studying these oscillations, scientists probe the behavior of matter in strong gravity, potentially constraining the neutron star radius and the equation of state. Although interpretations remain debated, the presence of these oscillations highlights the richness of accretion dynamics. Accretion episodes can be transient. Many X-ray binaries alternate between quiescent states, where the accretion rate is low, and outbursts, where the rate suddenly increases by several orders of magnitude. These outbursts are thought to be triggered by instabilities in the accretion disk, which periodically switches between hot, ionized states and cool, neutral states. During outbursts, the system brightens dramatically in X-rays, allowing detailed observations. In quiescence, the faint emission reveals the thermal state of the neutron star's surface and crust, which can be compared with models of heating and cooling. The accretion process can also ignite thermonuclear explosions on the surface, producing type 1 X-ray bursts. When enough hydrogen or helium accumulates on the surface, it ignites unstably, releasing energy in a runaway chain of nuclear reactions. These bursts last tens of seconds and will be examined more closely in the next section. The occurrence of such bursts is a direct outcome of accretion in low-mass X-ray binaries and provides a unique probe of surface and atmospheric physics. Accreting neutron stars are laboratories for strong field gravity as well. Because matter in the disk orbits at significant fractions of the speed of light, relativistic effects shape the emission. Gravitational redshift alters photon energies, light bending affects observed pulse profiles, and frame dragging may influence the flow of matter near the surface. Observing and modeling these effects enables tests of general relativity in regimes inaccessible elsewhere. The observational diversity of X-ray binaries reflects the variety of accretion modes. Persistent systems accrete steadily from companions, while transient systems erupt episodically. Some show coherent pulsations, others show quasi-periodic oscillations, and still others display cyclotron resonance features in their spectra. Together, they demonstrate how the simple act of feeding a neutron star with matter can produce a wide array of observable consequences. Ultimately, accretion is one of the main channels by which neutron stars reveal themselves. It transforms invisible, compact remnants into some of the brightest X-ray sources in the galaxy. It reshapes their spin, alters their magnetic field configuration, and exposes their surfaces to observation. By studying accreting systems, astronomers gain both a window into the neutron stars themselves and a means of exploring the physics of matter in the presence of intense gravity, magnetic fields, and radiation. When matter from a companion star accumulates on the surface of a neutron star, the environment becomes ripe for unstable nuclear burning. This phenomenon produces type 1 X-ray bursts, among the most striking signatures of accreting neutron stars. The process begins as hydrogen and helium flow onto the star from an accretion disk. Gravity compresses this material onto the surface, where it forms a thin, dense layer. The pressure at the base of this layer increases as more material piles up. Temperatures rise to tens of millions of degrees, but at first the nuclear burning proceeds stably, consuming some hydrogen in a slow fashion. Eventually the conditions cross a threshold where burning becomes unstable. At that moment, a thermonuclear runaway ignites. The ignition typically involves helium fusion through the triple alpha process. In an instant, helium nuclei combine to form carbon, releasing vast amounts of energy. The runaway spreads rapidly across the neutron star surface, engulfing the entire layer in a matter of seconds. The energy released heats the surface to hundreds of millions of degrees, producing an intense flash of X-rays. Observers detect the sudden rise in brightness, which can increase by factors of 10 to 100 within a second. This is the hallmark of a type 1 X-ray burst. After the initial rise, the burst enters a cooling phase. The surface radiates away the stored heat, and the X-ray flux decays gradually over tens of seconds to minutes. The cooling tail provides valuable information about the star. By analyzing the spectrum during this phase, astronomers can infer the effective temperature and radius of the emitting surface. In some cases, the bursts are so luminous that radiation pressure lifts the atmosphere away from the star. This is called photospheric radius expansion. During such events, the luminosity reaches the Eddington limit, where radiation pressure balances gravity. Measuring this limit gives a way to estimate the mass-to-radius ratio of the star, offering constraints on the equation of state. The recurrence time of bursts depends on the accretion rate. If matter flows rapidly, bursts may occur every few hours. If the rate is lower, the intervals can be days. The properties of the bursts, duration, peak flux, and recurrence, provide clues to the composition of the accreted material. Systems accreting hydrogen-rich material show different burst behavior from those dominated by helium. This diversity reflects both the nature of the companion star and the details of nuclear burning on the neutron star surface. Longer bursts, called superbursts, also occur but are rare. These last for hours and are thought to result from the ignition of carbon at greater depths beneath the surface. Because the overlying layers are thicker, the ignition requires more accumulated material and higher pressures. The study of superbursts probes nuclear reactions beyond the standard hydrogen and helium burning, extending knowledge into carbon fusion under extreme gravity. Observing such events is challenging due to their rarity, but satellites such as RxTE, Integral, and NICER have recorded examples. The physics of bursts links nuclear astrophysics with observational astronomy. The chain of reactions during a burst follows the rapid proton capture process, or ARP process, in which nuclei rapidly capture protons and build heavier elements. This process moves through isotopes far from stability, many of which cannot be studied in laboratories. The light curves and spectra of bursts therefore provide indirect information about nuclear reaction rates under conditions not otherwise accessible. The bursts also affect the neutron star itself. Repeated burning heats the crust over time, changing its thermal structure. When accretion halts and the star enters quiescence, the crust cools, and this cooling can be observed as a gradual decline in X-ray flux. Comparing these cooling curves with models allows astronomers to study how nuclear reactions deep in the crust deposit heat, a process known as deep crustal heating. This connects surface phenomena with the long-term thermal evolution of the star. Observations of X-ray bursts require sensitive satellites. Missions like RxTE provided thousands of burst detections, building a statistical picture. NICER continues this work with precise timing and spectral capability. The variety of bursts, short, long, superbursts, reveals the range of conditions possible on neutron star surfaces. Each burst observed adds another piece to the puzzle of how nuclear physics operates in the presence of gravity 100 billion times stronger than on Earth. Some bursts show oscillations in their light curves. These burst oscillations are periodic variations at frequencies close to the star's spin rate. They are thought to arise from asymmetries in the burning as it spreads across the surface. Detecting these oscillations provides a way to measure the spin of neutron stars that may not otherwise show pulsations. The observed frequencies confirm that many neutron stars rotate hundreds of times per second. Thus, bursts not only reveal nuclear burning but also probe the rotation of the underlying star. Another phenomenon linked to bursts is photospheric radius expansion. During these bursts, the luminosity reaches the point where radiation pressure lifts the outer atmosphere. As the atmosphere expands, the observed temperature decreases while the apparent emitting area increases. When the atmosphere contracts again, the temperature rises. These cycles allow measurement of the Eddington limit and, when combined with distance estimates, provide direct constraints on mass and radius. Such measurements are among the most powerful tools for probing the dense matter equation of state. Type 1 X-ray bursts demonstrate the interplay between accretion, gravity, and nuclear physics. They show how a thin layer of matter on a neutron star can produce explosions releasing as much energy in seconds as the sun emits in days. They connect the microphysics of nuclear reactions with the macrophysics of stellar evolution and compact objects. By studying bursts, astronomers learn not only about neutron stars but also about the processes that govern element synthesis and the behavior of matter under crushing gravity. The continuous monitoring of accreting systems has revealed thousands of bursts across many sources, confirming that they are a common and robust phenomenon. Despite their small scale, confined to a thin shell on the surface of a star only 20 kilometers across, their brilliance makes them visible across the galaxy. They remain one of the clearest observational windows into the otherwise hidden surfaces of neutron stars. After the violent events of birth and the possible active phases of accretion, a neutron star continues to evolve thermally. Its long-term cooling is governed by the balance between energy lost as photons from the surface and energy lost through neutrinos from the dense interior. In the earliest years, neutrino emission dominates. Neutrinos interact only weakly with matter, so they escape easily, carrying energy directly from the core. As the star ages, the surface emission of photons in X-rays and ultraviolet light gradually becomes more important. Tracking this progression provides one of the most effective ways to study the interior physics of neutron stars, since the cooling rate depends on the processes occurring inside. The simplest channel of neutrino emission is called the modified Urca process. In this reaction, a neutron converts to a proton, electron, and antineutrino, or the reverse occurs, but with the assistance of a bystander nucleon to conserve momentum. This process is relatively slow but always possible, so it forms a baseline for cooling. Under certain conditions, however, a much faster channel called the direct Urca process becomes allowed. In this case, a neutron converts directly to a proton, electron, and antineutrino without the need for an additional nucleon. The direct Urca process requires that the fraction of protons in the core exceed a certain threshold, which depends on the equation of state. If this condition is met, cooling is dramatically accelerated and the surface temperature declines far more quickly. Observations suggest that not all neutron stars cool at the same rate, supporting the idea that some permit the direct Urca process while others do not. For instance, certain young neutron stars appear unexpectedly cold for their ages, implying rapid neutrino cooling. Others remain warmer, consistent with slower, modified Urca cooling. This diversity indicates differences in mass and composition, since more massive stars are more likely to reach the central densities needed for direct Urca. Superfluidity and superconductivity add further complexity. As described earlier, neutrons in the core may form a superfluid and protons a superconductor. When this happens, many neutrino emission channels are suppressed because the paired particles cannot easily participate in reactions. However, a new process appears, the breaking and formation of pairs. As pairs form or break, neutrinos are emitted, creating bursts of cooling. This effect can produce rapid changes in the thermal evolution at the moment when pairing begins. Observational evidence for such behavior comes from the neutron star in the Cassiopeia, a supernova remnant. Over just a decade, its surface temperature was observed to decline by a few percent, much faster than expected. This has been interpreted as the onset of neutron superfluidity in the core, providing one of the most direct pieces of evidence for such states in nature. The crust also contributes to thermal behavior. Nuclear reactions occur as the crust is compressed by ongoing accretion in binaries. These reactions deposit heat in a process called deep crustal heating. When accretion halts, the crust cools back toward equilibrium with the core. Monitoring the cooling of transiently accreting neutron stars in quiescence has provided important information about thermal conductivity and heat capacity. Some stars cool quickly, indicating high conductivity, while others cool slowly, suggesting additional heat storage or insulating layers. Surface emission is shaped by the thin atmosphere covering the star. Although only centimeters thick, the atmosphere modifies the spectrum of escaping radiation. A hydrogen atmosphere, for example, produces spectra that differ from a helium or heavy element atmosphere. Strong magnetic fields also alter the opacity and polarization of emitted photons. To infer surface temperatures accurately, astronomers must model these atmospheres carefully. This has been done for isolated neutron stars such as the so-called Magnificent Seven, a group of nearby, thermally emitting objects observed in X-rays. Their spectra provide relatively clean measurements of cooling without strong magnetospheric contamination. Cooling tracks can be compared with theoretical models to constrain interior physics. Standard cooling curves assume modified Urca processes only. Enhanced cooling curves include direct Urca and exotic particles such as hyperons or deconfined quarks. The data so far suggest that both kinds of cooling occur in different stars, reinforcing the idea that neutron stars span a range of masses and central densities. Another energy loss mechanism is the emission of neutrinos through Bremsstrahlung, where nucleons scatter off one another and emit neutrino-antineutrino pairs. This process is generally weaker but still contributes. In addition, strong magnetic fields can open new channels of neutrino emission, though these remain more uncertain. The inclusion of all these mechanisms in cooling simulations allows comparisons with observed surface temperatures at known ages, building a consistent picture. The measurement of ages comes from different sources. For young neutron stars associated with supernova remnants, the age can be estimated from the expansion of the remnant. For pulsars, the characteristic age derived from spin-down provides an estimate, though sometimes imprecise. Matching temperature with age on a cooling diagram then tests theory. Some stars lie well above the standard curve, remaining warm, perhaps due to ongoing heating mechanisms. Others fall below, indicating enhanced cooling. Heating processes can indeed alter thermal evolution. Magnetic field decay, especially in magnetars, injects heat into the crust, keeping the surface bright in X-rays far longer than would be expected from passive cooling. Accretion also reheats neutron stars, as described earlier. Even rotation may play a role. Friction between superfluid vortices and the crust can release energy. These processes must be accounted for when interpreting observations, since they can mask or mimic cooling signatures. The long-term endpoint of cooling is a cold neutron star emitting little detectable radiation. After millions of years, the surface temperature may drop below 100,000 kelvins, leaving emission primarily in the ultraviolet or invisible altogether. Such old stars become difficult to observe directly, though they may still be inferred through their gravitational or dynamical effects. The population of neutron stars in the galaxy is therefore far larger than the visible sample, but most are dark. The study of cooling is valuable because it links astronomical observation to nuclear physics. The exact rates of neutrino processes depend on particle interactions at high density, on the presence of superfluidity, and on the composition of the core. Observing how real stars cool therefore provides indirect but powerful evidence about matter under conditions that cannot be replicated on Earth. Each data point on a cooling diagram is a probe of nuclear physics at densities beyond those in any laboratory. In summary, within the scope of this section, the thermal evolution of neutron stars is governed by neutrino emission, photon emission, and heating processes. The modified and direct Urca processes, superfluid effects, deep crustal heating, and magnetic decay all shape the observed cooling curves. By comparing observations with models, scientists extract constraints on the properties of dense matter. The cooling of neutron stars thus serves as a natural laboratory, revealing how matter behaves under extremes of pressure and density over timescales of thousands to millions of years. When two neutron stars orbit one another in a binary system, they gradually spiral together due to the emission of gravitational waves. This in-spiral continues for millions or billions of years until the stars finally merge. The merger is one of the most energetic events in the universe, producing electromagnetic radiation, gravitational waves, and heavy elements. The physics of such mergers has been studied through theory and simulation for decades, but direct observations in recent years have provided confirmation and detail that were once only speculative. As the stars approach each other, tidal forces distort them slightly. Their rotation and orbital motion synchronize, and the emission of gravitational waves carries away orbital energy. The rate of energy loss accelerates as the orbit shrinks, so the stars spiral inward faster and faster. In the final seconds, they circle one another hundreds of times per second before colliding. The gravitational wave signal from this inspiral is a distinctive chirp, rising in frequency and amplitude until the merger. The detection of such chirps by LIGO and Virgo has provided direct evidence of binary neutron star coalescence. When the stars collide, several outcomes are possible, depending on the total mass. If the combined mass exceeds the maximum supported by neutron star matter, the remnant collapses quickly to a black hole. If the mass is somewhat lower, the remnant may survive temporarily as a hypermassive neutron star supported by rapid rotation and thermal pressure before collapsing. In some cases, the remnant may remain stable as a massive neutron star. Each scenario produces different signatures in both gravitational and electromagnetic waves. During the merger, large amounts of matter are ejected. Some of this matter is tidally stripped during the in-spiral, forming elongated streams. Some is ejected dynamically during the collision, while additional material can be blown off by winds from the remnant or the accretion disk around it. The ejected material is extremely neutron-rich, providing the perfect conditions for rapid neutron capture, or the R process. In this process, atomic nuclei rapidly absorb neutrons and then undergo beta decay, building up heavy elements such as gold, platinum, and uranium. For decades, astrophysicists suspected that neutron star mergers were a major site of R-process nucleosynthesis, and observations have now confirmed it. The electromagnetic signature of this nucleosynthesis is called a kilonova. As the ejected matter expands and radioactive isotopes decay, they release energy that powers a thermal glow. The light curve and spectrum of a kilonova depend on the amount of ejected mass and its composition. Material rich in lanthanides, a group of heavy elements, is highly opaque, producing redder emission that lasts longer. Material with fewer lanthanides produces bluer, faster fading emission. Observations of kilonovae provide direct evidence of element formation. The landmark event G.Yahon 708817 in August 2017 was the first detection of a binary neutron star merger by gravitational waves. Just seconds later, satellites detected a short gamma-ray burst, and over the following days and weeks, telescopes across the electromagnetic spectrum observed the evolving kilonova. The light curve showed both a blue component in the early days and a redder component later, consistent with the presence of both lanthanide-poor and lanthanide-rich ejecta. This event confirmed that neutron star mergers produce heavy elements and demonstrated the power of multi-messenger astronomy. Short gamma-ray bursts are among the most luminous explosions observed, and for years they were suspected to be connected to neutron star mergers. The coincidence of GW 170817 with a gamma-ray burst provided strong confirmation. The gamma rays are thought to arise from jets launched at nearly the speed of light during or after the merger. If the jet is pointed toward Earth, the burst is seen as an intense flash lasting less than 2 seconds. If viewed off-axis, the gamma-ray emission may be weaker or absent, but afterglows in X-rays, optical and radio can still be detected as the jet interacts with surrounding material. The physics of the merger remnant is complex. Simulations show that the collision produces violent oscillations, shock heating, and differential rotation. If the remnant avoids prompt collapse, it may emit gravitational waves at characteristic frequencies for tens of milliseconds. Detecting such post-merger signals would provide invaluable information about the equation of state, since the oscillation frequencies depend sensitively on the structure of the star. Current detectors are not yet sensitive enough to routinely detect post-merger signals, but future upgrades may make this possible. The accretion disk formed around the remnant is another important component. The disk can feed material onto the central object, powering winds and possibly launching jets that create gamma-ray bursts. The magnetic fields generated in the turbulent disk may reach enormous strengths, contributing to jet collimation and energy extraction. The interaction between the disk, the remnant, and the ejected material determines the observable outcome. Kilonova observations also provide measurements of cosmic expansion. The gravitational wave signal gives the distance to the source, while electromagnetic observations give the redshift. Combining these yields an independent determination of the Hubble constant. GW 1717 provided the first such standard siren measurement, complementing traditional methods using supernovae or the cosmic microwave background. With more events, this approach could help resolve current tensions in cosmology regarding the precise value of the Hubble constant. The rate of neutron star mergers in the universe has been estimated from both gravitational wave detections and the observed abundance of R-process elements. The rates suggest that such mergers are indeed capable of producing most of the heavy elements in the universe, though core collapse supernovae may also contribute under certain conditions. The balance between these sites remains an active area of research. Binary neutron star systems themselves are rare but not unknown. Several have been detected in our galaxy as radio pulsars in binary orbits. The double pulsar system, JZO 737 3039, is a notable example, with two pulsars orbiting each other every 2.4 hours. Observations of such systems allow precise tests of general relativity and provide laboratories for studying tidal interactions, spin evolution, and orbital decay. The measured orbital shrinkage in these systems matches the predictions of gravitational wave mission, providing indirect confirmation long before direct detections were made. The merger of neutron stars therefore ties together many areas of astrophysics: gravitational waves, gamma-ray bursts, heavy element nuclear synthesis, and cosmology. Each observation adds to the picture of how these collisions unfold and what they produce. Future detectors with greater sensitivity will expand the sample, providing opportunities to detect post-merger gravitational waves, study kilonova diversity, and refine measurements of cosmic expansion. The sequence from inspiral to merger to kilonova demonstrates how compact objects continue to shape the universe long after their birth. Through their collisions, neutron stars seed galaxies with the heavy elements that enrich planets and living matter. Through their signals, they allow astrophysicists to probe gravity, nuclear physics, and cosmology with a single event. The study of these mergers is still young, but it already stands as one of the most fruitful intersections of observation and theory in modern astrophysics. The detection of gravitational waves from neutron star mergers has opened an entirely new way of studying dense matter. Gravitational waves are ripples in space-time predicted by general relativity. They are produced whenever massive bodies accelerate asymmetrically. In the case of binary neutron stars, the continuous inspiral creates a characteristic signal. The amplitude and frequency evolution of this signal depend on the masses of the stars, their spins, and the way they deform under tidal forces. Observatories such as LIGO in the United States, Virgo in Italy, and CAGRA in Japan use laser interferometers with arms kilometers long to measure these minute distortions in space-time, smaller than the width of a proton. The inspiral waveform of two neutron stars encodes their masses with high precision. By fitting the observed chirp with templates calculated from general relativity, astronomers can determine the component masses of the system. This is how Jepwand 70817 was shown to involve objects between about 1 and 2 solar masses consistent with neutron stars. Black holes of such low mass had never been confirmed, so the identification of the components as neutron stars was secure. Tidal deformability is another key parameter measurable from gravitational waves. As the stars orbit, each one raises tides on the other. These tides modify the orbital motion slightly, imprinting a subtle phase shift on the gravitational wave signal. The size of the tidal effect depends on how easily the neutron star matter can be deformed, which in turn depends on the equation of state. A stiffer equation of state produces less deformability, while a softer one produces more. By measuring tidal deformability, gravitational wave detectors place direct constraints on the structure of neutron stars. The observations from GW 1017 ruled out the softest equations of state, which predict very compact stars. The merger itself is accompanied by a burst of gravitational radiation that is more complex and shorter in duration than the inspiral signal. In principle, the frequencies of post-merger oscillations could reveal the maximum mass and internal composition of the remnant. Current detectors are not sensitive enough to pick up these short-lived high-frequency signals, but future upgrades may allow such measurements. If detected, post-merger gravitational waves would provide a unique probe of matter at densities far beyond nuclear saturation. Gravitational wave observations also measure the inclination of the binary's orbit relative to Earth. This information, combined with electromagnetic observations, helps in interpreting the brightness of colonovae and gamma-ray bursts. For example, if a gamma-ray burst appears faint, it may be because the jet is viewed off-axis, not because it is intrinsically weak. Knowing the orientation from gravitational waves resolves this ambiguity. The precision of gravitational wave astronomy depends on the sensitivity of detectors and the number of events observed. With each new detection, the statistical power grows. Already, events such as GW190425 have hinted at unusual systems, including binaries with total masses higher than typical galactic double neutron stars. These suggest diversity in binary populations and may indicate different evolutionary pathways. The combination of gravitational wave distances with redshifts measured from electromagnetic counterparts provides a method to determine the Hubble constant. This standard siren approach is independent of traditional methods such as Cepheid variable stars or the cosmic microwave background. With G/0817, a first estimate was made, though with large uncertainties. With dozens of future events, this method may resolve the current discrepancy between local and early universe measurements of the Hubble constant, a tension that has significant implications for cosmology. The joint detection of gravitational waves and light from G117G and 817 exemplified the power of multi-messenger astronomy. The gravitational wave signal pinpointed the time of merger and a rough location in the sky. Telescopes worldwide then searched the region, finding a new optical source in the galaxy NGC 4993. Over subsequent days, this source faded and changed color as expected for a kilonova. X-ray and radio emission appeared later as the outflow interacted with surrounding material. This sequence confirmed theoretical predictions and demonstrated that observing both gravitational and electromagnetic waves provides far more information than either alone. In addition to binary mergers, gravitational wave detectors can also constrain isolated neutron stars. If a neutron star has a small mountain or an asymmetric distribution of mass, it will emit continuous gravitational waves as it rotates. The amplitudes are expected to be tiny, but with increasing sensitivity, detectors may eventually reach the levels required. Such detections would directly measure deformations of neutron stars and could reveal properties of the crust and interior. Searchers have already placed upper limits on gravitational wave emission from known pulsars, showing that any mountains must be extremely small, only fractions of a millimeter in height. Another potential source is R-mode oscillations, global fluid waves in the star that could emit gravitational radiation. If unstable, these modes could limit the rotation rates of neutron stars, preventing them from spinning beyond a certain frequency. Although no direct detections have yet been made, ongoing searches continue to look for these signals in young, rapidly rotating stars. Confirmation would provide insights into the viscosity and superfluid properties of dense matter. Gravitational wave astronomy is still young, but its impact on neutron star physics has already been profound. The measurements of masses, tidal deformability, and merger rates are reshaping the understanding of dense matter and binary evolution. As detectors improve and networks expand, the number of detected events is expected to grow into the hundreds or thousands. This will allow population studies, comparisons across environments, and refined constraints on fundamental physics. In the future, space-based detectors such as the Laser Interferometer Space Antenna, or LISA, will extend gravitational wave sensitivity to lower frequencies, opening the possibility of detecting in spirals long before merger. Although LISA will primarily observe massive black hole binaries, It may also detect signals from compact stars in the galaxy. Combining ground-based and space-based observations would provide a full picture of compact binary evolution from early in spiral to final coalescence. The study of neutron stars through gravitational waves illustrates how a new observational channel can transform understanding. Once thought impossible to detect, gravitational waves are now measured routinely, and with them the interiors of neutron stars are indirectly explored. They complement electromagnetic observations and provide checks on nuclear physics models, general relativity, and cosmology. Each chirp recorded on Earth represents not just a distant collision, but a new piece of evidence about the fundamental properties of matter and space-time. Pulsars in binary systems provide natural laboratories for testing the predictions of general relativity. Their precise timing allows measurement of relativistic effects that are otherwise impossible to detect directly. Each pulse from a pulsar acts like the tick of a clock. By recording the arrival times of these pulses over years or decades, astronomers can reconstruct the orbit of the pulsar and its companion with extraordinary accuracy. Deviations from simple Keplerian motion then reveal relativistic phenomena. One of the most famous systems is the Hulse-Taylor binary pulsar, discovered in 1974. It consists of a pulsar and another neutron star in an elliptical orbit. Timing measurements showed that the orbit shrinks slowly over time, precisely as predicted by the emission of gravitational waves in general relativity. The rate of orbital decay matched theoretical calculations within a fraction of a percent. This was the first indirect evidence that gravitational waves exist, decades before their direct detection. The discovery earned the Nobel Prize in Physics in 1993 and remains a cornerstone of modern astrophysics. Another relativistic effect is Shapiro delay. When the pulses from a pulsar pass near the gravitational field of its companion, they take slightly longer to reach Earth. This extra delay depends on the companion's mass and the orientation of the orbit. Measuring Shapiro delay provides a direct determination of the companion's mass, and combined with other parameters, the pulsar's mass as well. This method has yielded some of the most precise neutron star mass measurements, including those near two solar masses that constrain the equation of state. Periastron advance is another test. In Newtonian gravity, the closest approach point of an elliptical orbit remains fixed. In general relativity, spacetime curvature causes this point to advance with each orbit. The rate of periastron advance depends on the total mass of the system and agrees with predictions of relativity. In binary pulsars, the effect is often measurable because the stars are massive and the orbits tight. Observing this advance provides another confirmation of Einstein's theory under strong field conditions. Some binary pulsars also show geodetic precession, where the pulsar's spin axis slowly precesses due to spacetime curvature. This changes the angle of the radio beam relative to Earth, gradually altering the pulse profile over years. Such observations give additional information about the geometry of the system and further confirm relativistic predictions. The double pulsar system JSO 737-3039 is an especially powerful laboratory. In this system, both neutron stars are observable as pulsars, orbiting each other every 2.4 hours. Timing the pulses from both stars allows cross-checking of measurements and testing of multiple relativistic effects simultaneously. Shapiro delay, orbital decay, periastron advance, and relativistic time dilation have all been measured in this system with high precision. The agreement with general relativity is remarkable, with no significant deviations detected. Future monitoring will tighten these tests further, possibly revealing small effects from alternative theories of gravity if they exist. Relativistic binary pulsars also probe the behavior of matter at extreme densities. By measuring the masses of neutron stars, astronomers constrain the maximum mass supported by the equation of state. If a pulsar is found with a mass above a certain threshold, softer equations of state are ruled out. The most massive, precisely measured neutron stars, close to 2.1 solar masses, come from such binary systems. These results complement radius measurements and gravitational wave observations, building a consistent picture. The precision of pulsar timing arrays arises from the stability of millisecond pulsars. These recycled pulsars, spun up by accretion in the past, rotate hundreds of times per second with exceptional regularity. Monitoring them over years allows timing residuals to be measured at the microsecond level. In binaries, such stability translates into extremely accurate orbital models. The data can detect even minute perturbations caused by relativistic effects. This is why binary pulsars remain among the strongest pieces of evidence for general relativity outside the solar system. Other timing effects include gravitational redshift and time dilation. As the pulsar moves in its elliptical orbit, its signals are affected by the changing gravitational potential and orbital speed. These changes alter the pulse arrival times in predictable ways. The combination of all these effects allows a system to be described by a set of post-Keplerian parameters, each corresponding to a relativistic correction. Measuring several of these parameters provides redundant checks on the theory. If general relativity is correct, all the parameters should correspond to a single consistent set of masses. Observations have confirmed this consistency across multiple systems. The use of pulsar timing to test general relativity also extends to the search for dipolar gravitational radiation, predicted by some alternative theories of gravity. Such radiation would cause orbital decay at a different rate than predicted by quadrupolar gravitational waves in general relativity. Careful monitoring of systems with pulsars and white dwarf companions, which have different gravitational binding energies, has placed stringent limits on such effects. These results severely constrain many alternative theories, reinforcing the status of general relativity as the correct description of gravity in the strong field regime. Pulsar timing continues to improve with advances in radio telescopes. Large facilities like FAST in China and Meerkat in South Africa, along with the upcoming square-kilometre array, will expand the sample of known pulsars and improve timing precision. This will extend the range of tests possible, potentially detecting tiny deviations or confirming general relativity with unprecedented accuracy. The interplay between pulsar astrophysics and fundamental physics is one of the defining features of neutron star research. By serving as clocks moving in curved space-time, pulsars translate the arcane mathematics of relativity into observable quantities. Each pulse that arrives at Earth carries the imprint of gravitational effects encountered along its path. Careful measurement and analysis transform these imprints into constraints on the laws of physics. Thus, binary pulsars not only reveal the masses and behaviors of neutron stars, but also serve as cosmic laboratories for gravity itself. Their continued observation is expected to sharpen tests of relativity, probe for new physics, and refine knowledge of the dense matter inside neutron stars. With each improvement in data and analysis, the link between astrophysical observation and fundamental theory grows stronger. Despite the immense progress made in studying neutron stars, many fundamental questions remain unanswered. The most significant uncertainty concerns the equation of state of matter at densities several times higher than those inside atomic nuclei. Observations of masses and radii provide constraints, but the exact composition of the core is still debated. Possibilities include nucleonic matter only, mixtures with hyperons, condensates of mesons, or even deconfined quark matter. Each possibility predicts different maximum masses, radii, and cooling behaviors. Discriminating among them requires more precise measurements and continued development of nuclear theory. The maximum mass of neutron stars is one of the key open questions. Observations have established that stars of around 2 solar masses exist, but whether nature allows heavier ones remains uncertain. If stars significantly above 2 solar masses are discovered, then only the stiffest equations of state will survive. If no heavier stars are found, the true maximum may be close to the current observational record. This value determines the boundary between neutron stars and black holes and affects how remnants of mergers evolve. Gravitational wave detections of high-mass systems will play an important role in resolving this issue. Another puzzle is the origin and evolution of magnetic fields. The existence of magnetars shows that fields can reach quadrillion Gauss strengths, but it is not clear how such fields are generated or sustained. Dynamo processes during the proto-neutron star phase are one possibility, requiring rapid rotation and convection. Fossil fields inherited from the progenitor star are another. How fields decay over millions of years, how they influence crustal fractures, and how they interact with superfluid vortices in the core are all active areas of research. The answers bear directly on the diversity of neutron star classes and their observed behaviors. Fast radio bursts represent one of the most intriguing mysteries. These are bright, millisecond flashes of radio waves that originate at cosmological distances. Their immense luminosities suggest compact energetic sources, and magnetars are leading candidates. The detection of a fast radio burst from the galactic magnetar SGR 1935+2 154 in 2020 strongly supports this link, but the diversity of fast radio bursts leaves open the possibility of multiple origins. Some repeat, some do not, and their environments vary widely. Determining whether all fast radio bursts come from magnetars, or whether other mechanisms such as neutron star mergers or interactions with black holes contribute, remains an urgent challenge. The phenomenon of glitches is also incompletely understood. Although superfluid vortex motion provides a general explanation, the details of pinning and unpinning, the role of crustal impurities, and the coupling between the crust and core are still unclear. Glitch activity varies widely among pulsars, with some showing frequent large events and others being stable for decades. Understanding this diversity may reveal more about the microphysics of superfluid matter and the structure of the crust. The mechanism of radio emission in pulsars continues to resist a complete explanation. Coherent radiation processes are clearly required, but the precise plasma instabilities and conditions remain debated. Observations of polarization, subpulses, and nanosecond-scale microstructure provide clues, yet no single model has gained universal acceptance. Since radio emission is the primary way pulsars are discovered and studied, solving this problem is central to interpreting all pulsar data. Neutron star cooling also presents uncertainties. While the rapid cooling observed in Cassiopeia A is consistent with the onset of neutron superfluidity, alternative explanations exist, and the sample of young neutron stars with reliable temperature measurements is small. Determining whether enhanced cooling through direct Urca processes or exotic particles like hyperons occurs in some stars requires more data. Similarly, the role of magnetic field decay in heating magnetars and its contribution to persistent X-ray luminosities is not fully quantified. The relationship between neutron stars and their environments raises further questions. Some supernova remnants show clear central compact objects that are thermally emitting but lack pulsations. These central compact objects challenge the standard categories of pulsar or magnetar. Their thermal emission and lack of strong magnetic field suggest a different evolutionary path, possibly involving buried fields that may re-emerge later. The discovery and study of more such objects will clarify whether they form a distinct class or represent transitional stages. The diversity of neutron star populations across the galaxy is only partly known. Radio surveys have found thousands of pulsars, but selection effects mean many remain hidden. Beaming geometry excludes those whose beams do not sweep Earth. Older stars with weak fields are faint and difficult to detect. The true number of neutron stars in the Milky Way may be 100 million or more, yet only a fraction are catalogued. Understanding the population as a whole is important for modeling binary evolution, merger rates, and galactic chemical enrichment. Another major uncertainty lies in the connection between neutron star mergers and short gamma-ray bursts. While GW 170817 confirm that mergers can produce these bursts, not all short bursts are necessarily from mergers. Some may originate from magnetoflares or other phenomena. Determining the fraction attributable to mergers requires continued multi-messenger observations. The geometry of jets, the conditions for successful jet breakout, and the diversity of afterglows all complicate interpretation. The future of neutron star research will depend heavily on new instruments. The next generation of gravitational wave detectors, such as Cosmic Explorer and the Einstein telescope, will detect thousands of mergers per year and measure tidal deformability with high precision. X-ray missions with improved timing and spectral resolution will refine radius measurements. Radio arrays like the Square Kilometre Array will discover tens of thousands of new pulsars, including many in binaries that will serve as laboratories for gravity. Together, these facilities will transform the landscape of neutron star science. Beyond astrophysics, the study of neutron stars impacts fundamental physics. They probe the behavior of quantum chromodynamics at densities inaccessible to colliders. They test general relativity in strong fields. They connect nuclear experiments on Earth with astronomical phenomena. Every advance in understanding neutron stars strengthens the link between microscopic and cosmic scales. In this final, scope-limited reflection, the unanswered questions highlight the frontier of research. What exactly lies at the center of a neutron star? How high a mass can nature sustain before collapse to a black hole? What mechanisms power fast radio bursts? How do magnetic fields evolve and decay? And how can laboratory nuclear physics, gravitational wave astronomy, and electromagnetic observations be unified into a coherent description of matter at its limits? Each question drives ongoing work, ensuring that neutron stars will remain at the center of astrophysics and fundamental physics for decades to come.